Welcome to my talk about Piranha Cloud and GlassFish and all things about fast Java. But first, before I start talking about fast Java, let me remind you why we have application servers and how fast or slow they are. The main thing about application servers, because that's where I'm heading to. I'm starting from application servers, which were a traditional way how we start applications. For many people now, they are not modern anymore, but there are still usages there. And I want to get to more modern ways how to run Java and show that Java can really have a fast startup, even if you use some frameworks, even if it's based on Jakarta EE. Which is not very common, or wasn't very common a couple of years ago. So first thing, why we have application servers? In the past, at least, they were meant to be a reliable way to run applications. They were built to be robust with clustering support, a lot of management features, and they were designed to start once and not restart very often. Even before, like long time ago, it was a habit to deploy multiple applications on the servers, and servers were meant to stay there running while the applications are restarted. Some of them are running for a longer time. Some of them are redeployed with a new version or restarted just for some configuration or update. It's not like that anymore in many cases, but still application servers have their value. But because of their nature, they are slow to start because they were not designed to be fast to start. They were designed to run reliably once they are started. Before we had application servers, maybe some people remember that used to start in minutes and it was really a pain. Now modern application servers don't take so long to start, but it's still an issue in some cases. Let's have for comparison, let's have a look at an application server like GlassFish, and how long it takes to start, and not only to start but also serve the first request after the application is deployed, because that also takes some time. So I'll start with a sample application. It just loads a simple servlet and responds in a browser with some hello world message. But what I'm going to do is I'm going to measure how long it starts, just for a demo on my computer. And for you to have some picture of how long it takes to start a modern application server. So I'm running it. It takes a couple of seconds. And with my script that I used to launch it, I'm also measure how long it takes for the first request. So now it takes about 9 seconds. Let me record this in my table here, where I will record some other ways also how to run the same application. So first, just for record, it's 9 seconds. It's a bit slower now when I'm streaming through Zoom. If Zoom wasn't enabled, it would be more like 6 seconds, about almost half less. But yeah, it's not that bad. We were used to have minutes to start up. This is still okay. And just to show you the application, what it does, basically just still running. It basically just shows hello from GlassFish. I probably don't need to show you the code. It's just a servlet. For those who know what servlets are, it cannot get any easier. For those who don't, it's just a component that responds to a request that comes from the browser, sets hello message into the output and send a response, or produces the response result, which is then turned into the HTTP response in the browser. So now, when we come back, how we can get this faster? Because plain Java starts very fast. It doesn't take very long to start a simple program. Even if it starts an application or HTTP server, it's not very fast. I have a demo of a simple application. Actually, I think I have two demos. One is really a plain application with this. It cannot get much easier. It's a lot of syntactic sugar or syntactic boilerplate, but it basically just prints an hello message. If we create a simple server with just Java APIs, it would look like this. We create some socket that we listen to, and then when there is incoming request, we print. We need to print this HTTP header because we don't have an HTTP server. Basically, we just have a server, and the protocol is not bundled in it. It doesn't know the HTTP protocol, so we output the HTTP header for the browser to know that it's receiving the response and print the message. This is probably the most lightweight HTTP server, which just responds to anything with this constant HTTP response. If we try to measure this, even the server, let's compare that. Obviously, I think most of you expect that it will be almost instantaneous. It's 0.144. So if we record this to the same graph, this visualization of plain Java is almost invisible. So there's a huge gap between how long GlassFish or an application server starts before it can serve a request, and for how long just plain Java starts and can serve the request. So the main point of my presentation is to answer the question, can some runtimes, especially Jakarta EE runtimes or servers, can get anything close to these startup times? If the question is whether GlassFish can get close to those startup times, that's tough, but there might be some other alternatives that implement the same Jakarta EE, which are faster. That's because Jakarta EE is an API. It's not a library that just works like that you edit to your application. It's an interface which your application compiles against, but then it can run against multiple implementations, and you can choose those implementations. In ideal world, it doesn't really matter whether you use one implementation or the other. Your application should work. Although in real world there might be some differences, but for small applications, which we usually need to run fast and start fast, the chance that we will hit these differences between runtimes, which are incompatible, are very small. So in the best case, we can just replace. We can use something like application server, which I represent this here by a family car that can take a lot of people, the whole family, to a trip. Or if we want just to have a nice drive for a single person or maybe a couple, we can choose something else. Same with implementations. If we want to serve a big application with a lot of features and monitoring and whatever the application service provides, we can go with application server like GlassFish. But if we want the application to start fast and and we don't need all that functionality, we can use another runtime that can get us there. I'm starting with Eclipse GlassFish, which is an example of application server that's on one side, and on the other side I will continue with another example, which actually has roots in GlassFish. So it's a nice nice example how the Jakarta EE can evolve. Even the runtime, the same code can evolve from something that's designed to run for a longer time, but not for fast startups, to something completely opposite. So GlassFish server is a Jakarta EE full profile application server, which means it provides all the functionality of Jakarta EE, all the APIs and specifications. Is open source, and as other application servers, is designed to be robust. It can deploy applications, redeploy them, monitor. It provides thread pools, connection pools, a lot of monitoring probes. So you can get a lot just by using GlassFish and deploying your application. You don't need to add these things to the application. It's already in GlassFish, and you can also manage it easily. You can you have an administration console. You have a command line tool to administer the applications on the server, configure them outside of the application, which is actually nice because you don't need to recompile your application, and you can separate the configuration and setting up for production from your application codes. A little bit of history of GlassFish, because it's been here for a while. For a long time, it was supported by Sun Microsystems, which was later bought by Oracle. Then Oracle lost interest in, at least in commercial usage of GlassFish. So later it donated the code to Eclipse Foundation, where it's become a separate Eclipse Foundation project with a team behind it, with a community behind it, a community of contributors. And it's also supported now by multiple companies, which are more or less involved in the project itself. So it's still active and actively maintained, actively supported. It's just not by a single vendor like Oracle before, but it's the code is owned by the Eclipse Foundation, and there are companies working on it and providing support. In the past year, there was the latest GlassFish 7 major release, which brought Jakarta EE 10. Back then, GlassFish 7 was the first one to certify against Jakarta EE 10, and that made it possible to release the Jakarta EE 10 standard, which needs some implementation to provide it. And now it's still actively developed. Since GlassFish 7, the first release of GlassFish 7, it brought some new features. Even it brought more support for microprofile, some specifications, not all of them, configuration, JSON Web Token, REST client. It's being actively tested against newer Java versions, so it automatically adopted. It was prepared to adopt Java 21 when it was released, and now it runs on Java 21. It also provides some other optional Jakarta EE specifications which are not part of the platform, like MVC. And it also has a nice distribution of GlassFish, which is called Embedded GlassFish. It doesn't have all the administration features, but allows to embed the GlassFish itself into an application, run your application without installing GlassFish and deploying it on GlassFish. And it actually can shorten startup times. So let me show where we can get just by using GlassFish embedded. The same application, just with GlassFish embedded, looks a little bit more complicated because we need to start GlassFish from our application. So besides having the servlet, which is more or less the same, We have, here are two variants of the same application. We can have a look at this one. It's just a standard main method, so no magic here. You can start this as a plain Java program that initializes a GlassFish object, configures the GlassFish server, prepares the deployment, so it needs to assemble the application together with all the classes, dependencies in jars to let GlassFish know where it can find them. And then we deploy the application from our code. The same thing for the other example, is just a different way how to package the application, where to find the resources. So let's see now how fast this is, if it can get faster. Where we have it, here we have here. So I'll run it with this command. And this command will again start the same application, but with embedded GlassFish, and measure how long it takes until the first request is I don't have something in the application. Maybe I haven't built it. Okay, I'll try the other variant. Maybe I made a mistake in my demo. So I'll try the other variant that packages the application in a different way. That one works. So here with embedded GlassFish, I got from 9 seconds to 6 seconds. And that's a real benefit of GlassFish, not just a coincidence. But if I didn't run Zoom, I would get to similar comparison even better, because with GlassFish embedded I usually get to 3 seconds, and GlassFish server I get to 6 seconds. So mostly when I tested this, the startup time decreased by half. Just with using embedded GlassFish with the same application, it just skips some features, doesn't load everything, and then it's comparable even to some other frameworks like Spring Boot, which is a bit faster, but not that fast. With Spring Boot with the same application, it's more or less 2 seconds compared to 3 seconds with GlassFish. If I run it with right now under this Zoom screen sharing, I would probably get it also with Spring Boot to some 4 or 5 seconds. So then it's more or less like 1 second here, 1 second there. But just with embedded GlassFish, we were able to reduce the startup time by half from regular GlassFish. What is very important to progress with GlassFish, or making something out of GlassFish that can start up fast and can be used in a different situation, or with different startup times, is that GlassFish is very modular. It's composed of a lot of components that provide specific Jakarta EE functionality. This is all integrated in GlassFish, but the integration is transparent and it can be done outside of GlassFish. In the past year, there was some effort to even modularize some parts that were entangled inside GlassFish. So some projects some new projects were created, like Transact for JTA, for transactions, EP0 for authentication, which were brought outside of GlassFish and nicely modularized so they can be used somewhere else. This is important for a new framework called Piranha Cloud. Piranha Cloud is a framework basically based on these components. It assembles these components in a new way, and the core of Piranha Cloud is a completely new servlet engine, which then runs all these components on top of it. This means that you can start with a very small core where you don't need anything, or you don't add anything you don't need, and then you only add those things you need for your application. Piranha Cloud is designed by some of the engineers that work also with GlassFish team. So there is some overlap, and both benefit from each other. Piranha Cloud borrows some modular components from GlassFish, and then GlassFish benefits from the knowledge of using these components in other words and improving these components for startup times. So then with Piranha Cloud, we can get just a subset of Jakarta EE APIs, but quite a big subset of Jakarta EE APIs, which are suitable for designing microservices like REST and creating REST endpoints connected to the database. More or less what you would need in microservices or in smaller services, and the subset or set of Jakarta EE APIs supported by Piranha Cloud is growing as the work on the project is ongoing. It's, as I said, it's extremely modular, so it starts as very simple core, and it's fast to start. I will show you in a second. So let's see how it works with Piranha Micro. With Piranha Micro, it's very similar to embedded GlassFish. It's even nicer to see the example. Okay, so we have again a servlet which does the same thing, just returns a different message. And then I also have two variants of Piranha. One actually supports class data sharing, which is an optimization I will show you later, and also initializes logging. So the framework is so minimalistic that it doesn't even use its own logging system or anything for logging. It relies on standard Java logging. But if you don't initialize and don't configure it, it will basically not log anything, or log just warnings and errors, no info messages. So to have something more realistic, initialize logging here by reading logging properties, which configures logging to also output some info messages. But the core is just the embedded Piranha engine, which is created as a simple object with a builder. We can provide several mappings here, no extra configuration in WebXML files or anywhere else. We can define it all here. So we defined the mapping for Piranha's simple servlet for the servlet to bind to the root context. And then we start Piranha engine. But we need something more, because this engine doesn't bring in the HTTP server. It's just to run things internally. So we can run it in our web application if we represent the HTTP request as an object. But if we want to turn a real HTTP request into an object that Piranha engine can process, we need to have a default HTTP server, and then an application server which actually communicates or turns the HTTP protocol into the HTTP objects. that Piranha can understand. So you can see how it basically works under the HUD, but it's still quite easy because it's just simple components that are just stacked onto each other. There's the HTTP server, which needs an application server connector, and then this connects to the Piranha engine. And then we can start the server, which will propagate all to the Piranha engine, and back Piranha engine will create an object, which will be in turn turned into an HTTP response. So when we start this, let's see what happens. I have a simple example here with measurements. So I will run the application with Piranha, and with Piranha we can see that it's way below 1 second. It's 300 milliseconds around. So let's put it here. Yeah, I skipped Spring Boot, but I think it would be more like 4 or 5 seconds. So not much difference, but with Piranha Cloud we can see that there is a big difference between embedded GlassFish and even Spring Boot. If Spring Boot was even 4 seconds, let's put it there. Piranha application starts much faster, and now we can even compare it better to plain Java, which took us around 150 milliseconds to start, and Piranha Cloud, which initializes the HTTP engine, the same as our plain Java application, but it also initializes the HTTP protocol. It initializes the servlet engine and actually processes the HTTP request as a servlet. It just starts in more or less two times longer than the smallest Java application possible, and that's a huge deal. So by explaining you how the code works, I basically explained also the architecture of Piranha Cloud, or at least the part of it about the servlet container. The servlet container is at the core of Piranha Cloud, and it's very embeddable. You don't need anything. You can only start it itself. You don't need HTTP listener if you don't need it, really. There are cases where you don't need it. I will come to them later a bit. And if you need a HTTP listener, you can add it. If you need additional extensions, if you need to support a REST engine, you can add it there. Most frequently, or the supported way how to add REST engine is to add the Jersey servlet, which builds on top of servlet APIs. This is an existing servlet, which is also used by GlassFish. So there's no special extension points needed for Jersey. You just deploy it as a servlet, and then you configure Jersey, and it can serve REST endpoints. But there are then some other extensions which also built on top of Piranha Cloud own extension APIs. And these extensions are twofold. The Jakarta EE extensions are basically wrappers around components that are used in GlassFish, or directly servlets, as in the Jersey case. And then there are other extensions like Hazelcast to support HTTP session replication, and JNDI extensions to be able to define objects into a JNDI tree and then retrieve it from there. And you can write your own extensions because it's very simple to write extensions either with the Piranha API or with plain servlet extension points like listeners on servlet context initialization or application startup or things like that. Piranha Cloud also provides executable jars, so it's not only a library that you add to your application and you have to run it from your code. You can also run an executable jar from command line and then execute any compatible web application. So I could wrap my application with just a servlet into a WAR file, web application archive, and execute it with Piranha. And I would get similar end results, but the implementation, the runtime of Piranha would be a separate jar, and my application would be a separate WAR, which I can also deploy to GlassFish, Embedded or GlassFish server, or any Jakarta EE runtime I want to choose. These executable jars, there are a couple of them. They all bundle a smaller or bigger subset of what's available in Piranha Cloud. So you no longer have an option to really pick exactly what you need. But if it's okay to use one of the prepared distributions, then you can just choose whatever is there and run your application with that. If you need exactly to choose what you want, you're probably better with the embedded version, and then you have full control. So where this startup speed matters, that's a question that's easy to answer almost everywhere. But where it matters most is when you have smaller applications, smaller services, and it started to matter more in microservices world or microservices architectures, where big applications became split to small applications, and often these applications are restarted due to some problems, some health checks reporting some issues. Maybe there's some connection error to a database or something. And if the service is running Kubernetes, Kubernetes is usually set up to restart the services. Or if you want to redeploy all microservices or only some of them, it still matters how long it will take until you have a new version of application running, because there might be some downtime or some time involved in this release process that requires some attention. In serverless architectures, where you build a lot of functionality as serverless functions, it's even more important. The reason is that serverless functions basically can be started for every request that comes. That's possible, or they can be started for when multiple requests come at the same time and you don't have enough instances of your function running. Then when the function is running for some time, it can serve multiple requests as they come, but if it's not used for some time, then it goes down and then it needs to be restarted again. And then every time your small function needs to be started again, it takes some time, and that's usually just to serve one request. So you want to avoid these situations when your function is not ready, and just to serve one request, the user needs to wait for 5 or 10 seconds. So in these cases, Piranha or similar solutions might be very convenient because they can reduce the startup time under 1 second, and then sometimes the user waits 1 second. Most of the time they just wait a couple of milliseconds, and that second is tolerable if it doesn't happen very often, which it doesn't. So let's see if Piranha can be used in a serverless environment and how, and what is actually the advantages of Piranha in that environment. The main advantage of Piranha is that it's very bare bones. So if you want to create an AWS function or some other serverless function in some other cloud provider, you can easily take only what you need. And in serverless functions, you basically only need the engine of Piranha or any framework, because the HTTP stack is already provided by the cloud. What actually is called in your application is a method which already contains the translated payload from the HTTP response or from another event, which it doesn't have to be HTTP. This is turned into a JSON or a Java object, which is already prepared for you. You don't need to run an HTTP server or a broker connector or anything. You just get an event and your method is called. So anything else beyond the core engine is just not used and takes some time to start, slows your startup time, and also eats some memory, some resources which you actually pay for if you are in AWS environment. So in AWS Lambda, one of the means how to implement a function is to create an object that implements an interface. One of the interfaces that AWS API provides. In this case, it's handler request, and it accepts API gateway object, which is actually a representation of an HTTP request coming from the API gateway service. And for this to work with Piranha, we only need to translate it to something that Piranha understands. Piranha understands an HTTP servlet object, which we can build from embedded request builder, and we copy the relevant parts of the incoming object, like path from the URL to this request, or a body, message body, or message headers. In this case, I'm making things simpler. I just copy a servlet path, which should be just / the context root, and then take this object, which represents the incoming request, and call the engine. And that's it. The engine will give me another object, which is the response, and this response contains headers, status code, body, which I need to again map to the response type that AWS service understands. And this is everything I need to do. So one translation from AWS object to Piranha object, and then call Piranha, and then one translation back from Piranha object to HTTP object that AWS understands. With this, we get very fast startup times in AWS. If I try, let's try to launch the service. The instructions. So I have this service already deployed in AWS. What I need is just to invoke the function. And I will let AWS to measure how long it takes. So in this case, initialization duration is 500 milliseconds, which means it took 500 milliseconds to get our environment running. And this is including the JVM Java virtual machine, but not only that, it also creates basically the whole virtual machine, the operating system, which is very lightweight because AWS optimizes this for AWS Lambda. But you can imagine this is like a Docker container or virtual machine that is completely isolated. It starts the Java virtual machine, and within this init duration, it even runs some of our code. Because if we're clever, we initialize Piranha in a static object, and this code is actually executed only when the Java virtual machine is initialized. This is how AWS Lambda works. It will create our or load our class. It will not just it will just stop before running the method to handle a request. But including all this code, this is initialization, and if we run it as a separate static variable or initializing the static code, the engine of Piranha will get initialized only when the JVM is executed. If we did it in the handler request method, it would be executed and initialized for every request, which is really not very efficient because this is just a configuration and it can be reused for every request. So that's why we put it into a static variable, and then it's part of the initialization time. And then the rest, this duration, 50 milliseconds, is how long it takes for Piranha to actually process the request. It still needs some things to be initialized after the object was created, because if we run it again, we will see that for the second time it took just 2.5 milliseconds. So the first time, the duration, even the method takes a bit longer because it runs the request for the first time, and it still requires some things to be initialized after the Piranha engine is initialized. But the second time, if the function is already initialized, Piranha doesn't need to initialize anything again, and it will just process the request, and it takes a very short time. But if we take this initialization duration as our startup time, we should probably count also this 50 milliseconds until the response is served. So it's around 600 milliseconds. But this also includes not only JVM itself, but also the creation of the virtual machine. We get to a bit longer. Oh, it should be 0. And let's make it 600, 0.600. So we get to a bit higher numbers, but it's because AWS also counts creation of the virtual machine, and then it runs the Java virtual machine. So it's not easy to say how long it takes for Piranha and the JVM process to start. We can only infer it from how long it takes to start on our computer. So if the CPU assigned to the AWS function is more or less comparable to my own local computer, then it takes around, let's see here, around 300 milliseconds to start Piranha Cloud, and before that it takes around another 300 milliseconds to initialize the virtual machine. So together it's 600 milliseconds. One thing I haven't shown you is means how we can improve this startup time even more, and that's by different technologies. Locally, what works pretty well with especially small applications is class data sharing, available in OpenJDK, which actually allows you to run the application once, cache data about classes, about the bytecodes, and then store it in some index. And then the next time when you run it with this index, it will skip creating or generating data about bytecode, and it will improve the startup time. In AWS Lambda, there's another optimizations we can use. It's called Snapstart, and that's also something you can use locally, but I didn't see much improvement in these small applications. You get much more benefit in bigger applications. Snapstart or crack, which is the technology in the OpenJDK or in some JDKs. That is basically the core of the AWS Snapstart feature. It allows the application to again start first time and then basically hibernate it. So it will not store some information. It will store everything that is the whole state of the application. And next time it will just wake it up from that point. So after the request is executed, it will basically revert back to the state where the application was before handling the request, and it will execute the next request from that state and again. So always it rewinds the application to the state where it was before handling the request, so it can handle the next request from that exact same point. With these improvements, you can get some shorter startup times. I'm running out of time, so I will just show you what you can do with CDS locally. With CDS locally, you need to do 2 steps, and also your application needs to support this. So this is where this is coming to. Class data sharing in it basically just the only thing it does, it will stop the application before serving the request. So this is just to initialize the application and then stop it, store the index of about the bytecode, and then the next time you can start it with this index and make the fast startup faster. So if we do this, we need to run it with the CDS arguments. Here. So if you look carefully, I run the application with this CDS, which is the extra code I added there. And if this argument is there, the application will just initialize and then stop. And then there are arguments for the JVM to create the index of classes loaded during this time. So I'll run it. It created this file, this index. And if I run it next time with this index, now I will measure the time. So I use this index here. And now I don't use the CDS argument. So I run this application normally, but I provide the index of classes in the bytecode. And with this, I can get to 100 milliseconds, 180 milliseconds. So this is an example how you can use other JVM technologies besides what's in Piranha to improve the startup time even further. Okay. So with this, we can actually get very close to our plain Java application. This is with a small example application. Obviously, if you build bigger applications, the startup time will continue to grow, but it's a good starting position. And with bigger application, you can still more or less keep the startup time around 1 second. So with this, Piranha is actually ready for many deployments where you need faster startup time, including AWS Lambda deployments where you really need very small startup times. The only thing is what is missing currently is the integration with AWS handlers. And that's why I needed to do this translation between AWS object and Piranha object and back. If this translation is currently being worked on, so once it's ready, you won't need to do all this boilerplate. There will be probably just one method to call to translate the object here and there, or something like that. So that's about it. The conclusion is that Jakarta EE is not only application servers. Recently, there are many offerings. There's Piranha. There's also some other like Quarkus, Helidon, and some other frameworks similar more or less to what Piranha is trying to do. They have different approaches, but they have what they have in common is they are lean, small, They provide a lot of Jakarta EE functionality, but they have short startup times, and they can be used in microservices, AWS Lambda, especially those scenarios where you need those startup times to be short. I don't know. If you have any questions, let me know. I don't see right now anything in the chat. So if you don't have any questions, then thank you for your attention, and I hope you have some inspirations to try different engines, different frameworks, and hopefully with Jakarta EE in those frameworks, so that you don't need to learn the new API, how to use them all the time again, and you can reuse just one technology, but have different outputs and different options. Thank you very much for your attention.